Hello everybody. Today we are going to solve Leetcode question 1079 letter tile possibilities. We have n tiles given to us where each tile has a letter printed on it. We have to return the number of possible non-sequence, non-empty sequences of letters we can make using these printed letters. Let's understand this with an example. So we are given the string A, A, B. We have to generate all the possible non-empty sequences from this string, right? The uh, all the non-empty sequences will be of length 1. There will be A and B. Of length 2, there will be AA, AB, and BA. Of length 3, there will be AAB, ABA, and BAA. So there are 2 plus 3 plus 3. There are 8 total sequences, non-empty sequences that make up this that we can make by using the string AAB. So thinking of solutions for this, the simple solution that we can think of is using recursion and backtracking, right? So we can consider each string to be the possible starting point, right? So we can consider the string A to be the possible starting point, then we can consider the next A to be the possible starting point, and then we can consider B to be the starting point. If we consider A to be the starting point, we can generate all the possible string sequences that we can from this starting A, and then similarly we can do it for the next A and for the next B. One thing to consider here is we do not have duplicates here, right? So we do not have another A mentioned here because that will be a duplicate. We have already considered the letter A. So to store the result, we can use some sort of a hash set or a hash map, right? And with that we can omit the duplicates, right? So let's write uh, an example. Let's consider the same string AAB. Okay, there are 3 possible starting points. We can start with the letter A, we can start with a second A, or we can start with the letter B. So let's also use a hash set, right, to store the unique uh, combinations possible. So right now, initially we have an empty string, right? Let's have an empty string inside the set, and also along with that, let's add the letters A and B. So we add the second A, but because we have a set, it will not be included twice. Great. So now we have used the first point, right? Now let's add the second. Let's generate all the possible substrings of sequences of length 2. Okay. So of length 2, so we have considered the first A, so we can add the second A to this, or we can add the B to this, right? So let's mention them as A1, A2, so that distinguish them. A1, A2, B, A1, A2, or A1, B. So possible sequences from A2 will be A2, A1, or A2, B, and for B will be BA1 or BA2. So now when we add these to the sequence, we will add only the unique ones. So it will be A, B, and A and BA. So this one will be duplicates. Similarly, this one and this one are duplicates. Similarly, this is also duplicate. These two also are duplicates, so they'll only be considered once, right? Now let's generate all the substrings of all the sequences of length 3. So it will be A1, A1, A2, B, right? So the only possible sequence, then it will be A1, B, A2. For this again, it will be A2, A1, B, A2, B, A1, B, A1, A2, B, A2, A1. Again, seeing the duplicates, this and this are duplicates, this and this are duplicates, and these two are duplicates. Right, so they'll only be considered once, and we will add only the unique ones to the result. So we will have AAB, ABA, and BAA added to our result. So with this, we can generate all the possible sequences from the string, from the given string. To keep track of which characters have been used and which are not, we can maintain some sort of a Boolean array, right, with all false initially. And whenever we fill in, we use up a value, we just change the position of that to be true, right? Something like this. So once we use up A2, we will change the array to look something like this. For each index, we can keep track of which characters have been used and which are not. Talking of time complexity, the time this function will take to run will be in the order of n factorial, because for each index we are considering n different possibilities, and then once we have chosen one of the indexes, again we are looking at n minus 1 different possibilities, and then n minus 2 different possibilities, and so on. So it will be n factorial, and for each starting point we are going to have this uh, function run. So it will be n into n factorial, n for the different starting points and n factorial to find the different permutations of length n, combinations and permutations of length n. Let's write a solution for this. So we will have to keep a track of all the unique sequences. So unique sequences, let's store it in a set, and after everything is done, we return the length of the set, and we call a recursive function self dot backtrack self tiles. Let's pass and uh, let's pass an empty string, um, and also we need to keep track of the characters that we have used, right? So used positions, let's say it is false, length of tiles. Okay. Define backtrack self tiles, current, and used position. Okay, so first thing we do is we just push whatever current string we have into the set. So mix dot add current string, and for each of the possible letters, so we loop through all the we loop through the length of the tiles string, and if the character is already used, we do not do anything. Otherwise, we set the character as used. We call the function again, call the backtracking function. We pass the tiles, uniques, current plus tiles at I, Just positions, and after calling this, we just decrement. We just set the character to be unused again, so that it can be used in the later recursions. Right. So this is the backtracking function. So we just add whatever string we have into the unique set hash map hash set for each of the available characters. We just loop through and we just set the character as used. We call the function again and we set the character to be unused. So after everything is done, we just return the length of the set, but we have to return all the non-empty sequences. So we have to reduce one from this length because initially we are sending in an empty string, right? So, so the solution. Let's try to run the test cases. Yeah, looks good. Let's submit. Accepted. Let's think of optimizing this solution. So consider the strings of length 1 that we have generated, A1 and A2, so these ones. If you take a look at the different solutions that we have come up from starting with A1, right? So for this subtree, this subtree is exactly equal to this subtree. So the different possible combinations will be A1 of length 1, A of length 1, AA and AB of length 2, and then AAB and ABA of length 3. So it is the same in both of these cases. So from this, we can conclude that it does not matter which A we take, we just have to consider it once, right? So if we consider the A1s, any of these two A1s, it should be more than enough for our solution, right? So if in case there are duplicates, we can consider the character to be included once in our solution, and we do not have to call the function for the next character again, right? Okay, so let's look at some way of solving this. Let's keep this as a reference and try to solve. So we have the string AAB. So let's keep the count of these characters. If the count of A is 2, the count of B is 1. Okay. So initially we have an empty string, right? So we can consider any of the characters A as the starting point. So let's have the A as the starting point and let's have B as the starting point. Okay. So if we use up A, the count of these characters will be 1 and 1. The count of A will be 1 and the count of B will be 1. And if we use B, the count of A will be 2. Okay. Now, let's generate all these strings of length 2. So we can either use the A again or we can use the B. Okay. So now if we use up the A, the count of A will be 0 and the count of B will be 1. And if we use B, the count of A will be 1. This is the remaining character that we can use. And for this, it does not matter which A we use, we just have to use it once. So the count of A will be 1, right? And similarly, uh, for these sequences of length 3, we can just add this remaining B. So we'll have AAB and ABA. And so for this again, it will be BAA. Now, if we take a look, we just are creating all the unique strings possible. So this will be, the result will be A, B, length 1, AA, AB, BA of length 2, AAB, ABA, and BAA of length 3. So this will give us 8 different. Looking at the tree, we can again notice one thing. We do not have to keep the track of the character count. We do not have to keep the track of the string. Well, right? We just are looking at the set that we have created with all the character combinations, and we can just use that. Let's create the recursion tree without using these strings. Initially, we have a count of A as 2, count of B as 1. Now let's call the recursion. So we reduce the count of, we can either reduce the count of A or we can reduce the count of B. If we reduce the count of A, the string will be, with the remaining available characters will be this or this. Then again, it will be this or this, and then again it will be empty, empty, empty. So we can use this instead, and we can count the different strings without using actual strings, right? So let's write the solution for this. Let's create the character count hash map. So we'll use the counter function to count all the different characters that we have in tiles, and let's call the function. And this should be tiles count, right? So let's initialize the um, total characters that we can create equal to 0. So for each character, so from a value in character count dot items, if value is greater than 0. So if the value is greater than 0, this means we have characters available and we can use that character. So we can increment total, so we can use up this character in our string, and we have to reduce the value of that character now. Character count k minus equals 1. We call our backtrack function self dot backtrack tiles and character count. And after the function is done, we again make the character available. Okay. So whatever result we get in this function, we again add this to the total. And after all the calls are ended, we just return the total. And this function will return the count directly. Call this function. Should be tiles. Okay. The test cases are passing. Let's submit it. Okay. So this looks good. The time complexity of this will be in the order of 2 to the power n, because we have, let's consider n to be the length of the character count array. So at each position we have two possibilities. We can either take it or we do not take it. So this will be 2 to the power n, and which is much better than the earlier solution that we had. Thank you.